Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. One of the nice features of Hilbert schemes is that it comes with an object for free called the universal family. In this video, I wanted to give you a quick introduction to this gadget and also show you why it's interesting and useful. I want to start with an example of a universal family, and it's something that hopefully, if you've seen a little bit of algebraic geometry, you've seen before. The example is going to be the projective space, and in this setting we want to work over an algebraically closed field K. And the projective space Pn I want to look at here, I want to view as a Hilbert scheme. And in this case, the Hilbert scheme I want to look at is the following. I want to look at the object which is n+1 dimensional K space. Okay, so that's an n+1 dimensional vector space over K. And I want to look at Hilbert n of this. So I want to basically look at all the Hilbert scheme of n-dimensional subspaces of this n+1 dimensional space, or better still, the one-dimensional quotients. And I'll denote the quotients of this V with a letter like L. So from that, I want to look at its universal family, and it turns out it's going to coincide with something called the tautological line bundle, which is often denoted O of 1. So this is something that hopefully you've seen before, but if not, I will go through and tell you what it is here, because it arises very, very naturally in the theory of Hilbert schemes from this point of view. Okay, so let's just see what's going on. Okay, so we're going to consider for each closed point P inside this projective space Pn, right? We want to view this Pn as an element of this Hilbert scheme. So this P really just means a one-dimensional quotient of this V. So that P is really just a one-dimensional quotient of this V. So it's some V mod some n-dimensional subspace WP, and I'll denote it as LP. So for each closed point P, it really is just an LP, but so that you know that we're thinking about this in terms of a quotient of V, I'll write it with a different letter LP like that. So basically the universal family is looking at all of these quotients, okay? So you want to look at the family of all of these LPs. And you want to think of this, of course, as a function from P to LP. Okay, so for every point P on Pn, you have this one-dimensional vector space. And so, of course, since you have that, and of course, this will also vary smoothly, okay, you get a line bundle. I'll denote that line bundle with L, and it's also denoted in sheaf theoretic notation with O of 1, okay? So for every point P on this projective space, okay, you have a one-dimensional vector space, that's LP, this one-dimensional quotient of this V, and that one-dimensional vector space will vary over this Pn, so you get a line bundle, okay? So you get more than just this line bundle, in fact. Remember, this line bundle is a quotient of V. So you have this trivial line, vector bundle rather, on Pn. It's going to be V cross Pn. And you also have, since LP is a quotient of V, you can put all of these quotients together to get a quotient of this vector bundle V cross Pn onto this line bundle. Okay, so that just means that above each point of Pn, say little p, okay, this vector bundle just looks like V. And so this map at that fiber, at that point P, is just going to be V surjects onto V mod WP, which is LP. Okay, so that's what you get. And of course, since that's fiber-wise surjective, you get the surjection of vector bundles. Okay, so in sheaf notation, we can do all of this as well. This L here is a sheaf O of 1. And what is this V cross Pn? What is the trivial vector bundle here? So I guess one way to write it is that the trivial line bundle is just the structure sheaf OPn. So we need to tensor this by K with V. And of course, since V is just n+1 dimensional vector space over K, this is just n+1 copies, okay, the direct sum of n+1 copies of the structure sheaf here. So this is the first example of a universal family, okay, and it corresponds to this Hilbert scheme here, the Hilbert scheme of one-dimensional quotients of this n+1 dimensional space, which is, if you like, sometimes the definition of projective space in algebraic geometry, at least as Grothendieck set it up. Okay, so let's generalize this situation and talk about universal families. So this is a very, very general idea, and unfortunately, I can't give you a definition which is rigorous, which covers all the different cases that can happen, okay? But the basic idea in all of them is the same, and I want to tell you what that is and then show you some more examples. So hopefully that if you see it in your mathematical adventures, you'll be able to recognize it. Okay, so what's the basic idea? Okay, so we're going to start with some object M, right? And we look at some sort of quotients of that. Some H is some Hilbert scheme of quotients of this. So that means for each point, closed point H inside big H, or you'll have some quotient NH. And basically, the universal family is just a set of all these quotients. You put them together. Okay, so it's a set of all this NH, but you put them in the family, so it's going to be a function from this H, this Hilbert scheme H, to this NH. That's how you want to think of it. And you put them together in various ways. So in this case here, for example, this is exactly what you see here. H is the Hilbert scheme of one-dimensional quotients of this Kn plus 1. So you put them all together here. P goes to LP like that. Here it's H goes to NH. And how you put them together will depend on the setting. So here you can put them together to get your whole line bundle and also a surjection of vector bundles. Here you see you get an invertible sheaf, okay, and here a surjection of locally free sheaves, okay. So not only do you get this universal family, okay, you also get a universal quotient, which you can kind of think of as, well, the kind of trivial version of M at every single point over H, so M cross H, if you like. And that, to some extent, surjects onto this family N of these. Okay, so that's the basic idea, and let's have a look at it in some other settings. And I want to look at it in the original Hilbert scheme setting. Okay, so sometimes the Hilbert scheme, as I've kind of defined it here, parameterizing quotients, is called the quat scheme because it parameterizes quotients. Hilbert was looking at a slightly more specific situation. So let me tell you what that is now. Okay, so here X is going to be some variety over our algebraically closed field X. And we'll look at the Hilbert scheme of X. Often we'll also put in some numerical invariant, but let's just leave that for the moment, okay, since it won't come into what I'm going to tell you. So what are the points, the k points of this Hilb X? Okay, so let's suppose H is a k point of this Hilb X, or close point. Well, basically, it's going to be given by some ideal IH of the structure sheaf OX. Okay, so it's an ideal sheaf like that. And remember, the ideal sheaves inside here also correspond to the closed subschemes of this X. So you get the closed subscheme ZH, which is just basically the zeros of the ideals here, but thought of as a scheme. So this will be a subscheme of the X, okay? And then, so this is rather nice. So I guess normally you should really look at OX mod IH. What's OX mod IH? Well, OX mod IH is actually just the structure sheaf, okay, naturally isomorphic to the structure sheaf of this closed subscheme. Okay, and when you write it like this, you also say how it is a closed subscheme of X. Okay, so this is quite strongly related to the quotients. Okay, and in this case here, whereas here we were looking at the family of quotients, H goes to NH. You see what happens is we've applied here the algebra geometry duality. So instead of looking at quotients of this OX, okay, we look at subschemes of this X. So here, the universal family sends this H to this universal subscheme, okay, so these ZHs, these subschemes instead. Okay, so let's look at two examples so that hopefully this idea is clear, and it's a very, very nice idea. So the first one is one that if you've looked at my video on lines on a cubic surface, you would have seen this used actually. Okay, so we're going to look at the Hilbert scheme of lines L inside P3. You can view this various ways, but one way to think about this is as two-dimensional subspaces of four-dimensional space, or two-dimensional quotients of four-dimensional space. So this is the Grassmannian 2, 4. okay? Two-dimensional subspace or four-dimensional space. Whatever it is, this is something that you can look at the Hilbert scheme of lines L inside P3. And what we want to do here, we want to look at the universal family. So that means just the set of all the lines, but you want to think of this as a function over this Grassmannian, okay? So for each element of this Grassmannian, this Hilbert scheme, I give you that line, okay? So what's the universal family here, okay? So here we're going to look, H is my Hilbert scheme, that's the Grassmannian. Okay, so for each L here, I fix that. What I'm going to put inside there, I'm going to put above that the whole line. So I'm going to put inside there the set of all points X, where X is inside the line. So this universal family here, okay, what is this universal family? It's just a subset of P3 cross H. Okay, it's a subset of P3 cross H. And what subset? In fact, it's going to be a closed subscheme. Okay, so what closed subscheme of P3 cross H will it be? Okay, well, the easiest way to think about it is over each point of H, where H is this Grassmannian here, okay, that corresponds to a line. So we're going to have just the points of that line. Okay, so as you vary over the points of this Grassmannian, this H, okay, you'll get this line and it'll vary over all of the lines inside P3. Okay, so that's an example of a universal family. Okay, and it sits inside the P3 cross H. That's the, so there is a dual version of this. Okay, so here you have the universal quotient. Here you'll have the universal sub-object. Okay, so Z, the universal sub-object will be U there, and it sits inside the product. So here the product is P3 cross H. Okay, so that's something that you have. Okay, so let's look at another example, which is perhaps a little bit less abstract. Okay, and this one here I'm going to look at is going to be, I'm going to look at A1X, that's my variety. Okay, and what subschemes that I want to look at here, I'm going to look at the ones which are basically linked to subschemes, the Hilbert scheme of 2 points on A1X. Okay, so what was that Hilbert scheme? So it turns out that that Hilbert scheme is just isomorph to the affine plane, okay, say with parameters A and B. So how did that go? So remember what we're going to do when we look at this Hilbert scheme here. The way we actually define it is we're going to look at ideals inside the coordinate ring, so in ideals in the polynomial ring Kx, okay, such that they are codimension 2. Okay. Now all the ideals inside the polynomial ring, remember, it's a principal ideal domain, so these are given by some monic polynomial which generates that ideal, and if you want the codimension to be 2, you need it to be degree 2. So the elements here essentially correspond to the ideals generated by a monic polynomial of this form, x squared plus ax plus b, and the a and b can freely vary, and as a and b varies across all possible scalars, okay, you will sweep out the whole of this Hilbert scheme. Okay, so there's the Hilbert scheme, is basically A to AB. Okay, so what's the universal family? So the universal family, it will sit inside the product. Okay, so the product here is the product of this H with this A to AB. And of course, that's just three-dimensional space. A3 with coordinates X, A, and B. Okay, and what is the universal family inside here? It'll be some sort of subscheme of this. So it's carved out by polynomials. And in fact, in this case, it's just carved out by one polynomial, x squared plus ax plus b equals 0. Okay, so this is an equation in the three variables, x, a, and b. So it will define a surface inside this three-dimensional space. Okay, and what you can do is that this surface, you can project this surface onto the AB coordinates, this AB plane. Project onto AB plane. So remember the AB, okay, they parameterizing all these subschemes, these length 2 subschemes, or these codimension 2 ideals, okay. So for each pair of points AB, you can look above that, okay, and that's going to give you, you fix the A and B. If you fix the A and B, you will have this quadratic here, and it defines some ideal, and hence it'll define an equation in A1x. So basically, it's going to give you 2 points in A1x. So for each AB, you'll get 2 points in A1x. And as if you vary these 2 points, of course, the roots of these will change, okay? So as you vary that, okay, you will get the universal family of 2 points on A1. Okay, so that's the universal family. And you can really see here that this object, it's still a variety, okay? So it's rather nice in that way. Okay, so hopefully you've got a little bit of an idea of what the universal family is in various settings. And hopefully these examples also show you that it's a useful object. Okay, so the line bundle is absolutely fundamental when you try to study PN because it allows you to study maps into projective space. Okay, and this is also something that, well, if you were to define PN in other ways, right, you can ask, well, what are the line bundles on it? And one of the things is that, well, if you realize that this is a Hilbert scheme, then you get a line bundle for free. And in this case, it will also turn out to be an interesting line bundle. Okay, so it gives you a line bundle for free rather. Here we've looked at this universal family, and here we've used this to study lines on a cubic surface. But I want to give you another application which I think is extremely interesting. Unfortunately, I can't give you all the details, but I can give you a bit of a flavor for why universal families are very important in mathematics. Okay, and the application is to the McKay correspondence. So I can't go through the McKay correspondence in detail, but if you like, you can look at my video on the McKay correspondence and find out more. So let me just review some of the elements that are in the McKay correspondence. So what's going on? So the setup is as following. We're going to start with a finite subgroup G of SL2. Since it's a subgroup of SL2, okay, so these are determinant 1, 2 by 2 matrices, okay, which act on two-dimensional space and hence act on the X and Y, okay, or the vector space generated by that, and hence on this polynomial ring. Okay, so G acts on this, and that also means that since G acts on this by algebra automorphisms, you get the skew group ring KXY star G. Okay, and I'll call that A. And this KXY is a module over this KXY star G. This is the skew group ring. Okay, and basically what that just means is that firstly, of course, it's a KXY module. You can multiply by scalars inside here. So essentially, this is KXY linear combinations of elements of the group, except for they skew commute. The elements of the group skew commute through here by the action. So you can act by KXY certainly on this, and you can also act by the group. And this action by the group is compatible with how it acts on here as well. Okay, so that's what you have. Now, given this data, what you can do is that this is the coordinate ring of the affine plane A2 with coordinates X and Y. And you can look at the G orbits of that. So that's going to be some variety A2 mod G, and it's going to be, in fact, a singular surface. And the singular surface here is called a Kleinian singularity, and it's also called a Duval singularity. Now, what's really nice is that, well, to study this, generally in algebraic geometry, you look at the minimal resolution of this surface singularity, and here we can express this as a Hilbert scheme. Okay, so what is it? It's the Hilbert scheme of certain quotients of KXY. Okay, I haven't written what the numerical invariant that I want to put here is, but I'll write it in over here. Okay, so which Hilbert scheme are we looking at? So we're going to look at this KXY as an A module. So we're going to look at A module quotients of this KXY. We're not going to look at all the A module quotients of this KXY. The ones we're going to look at are going to be isomorphic to, firstly, KG. So firstly, KG is going to be a sub-algebra of this A. So this is also a KG module. And so if you have an A module quotient, you'll have a KG module structure on that. And as a KG module, you want that quotient to be isomorphic to KG. Okay, so in particular, since it's isomorphic to KG, the dimension of that quotient as a vector space over K is going to be order of G. Okay. So you look at all these quotients of this kxy, okay, and they're going to be order of g dimensional, all these order of g dimensional quotients of kxy. And of course, the universal family is you just look at all these quotients. Okay, so on this h, okay, for each point, you're going to look at this order of g quotient of kxy. And of course, it has to have this extra property that it's isomorphic as a kg module to kg. Okay, so you do that for each and every single point on this h. So you'll get some vector bundle firstly on this h, and the rank of that vector bundle is the order of g. So the universal family U is firstly a vector bundle on h, and the order is going to be, or the rank rather, is the order of g. But the other thing is that each of those modules is actually an A module. Each of those vector spaces, so each point A acts. So A acts on the whole thing. So you can think of this universal family as both an A module and a vector bundle on H. So A will act on it. And so this is the key point, okay? So what are we going to get from this universal family? Okay, this universal family, firstly, is going to be an object that kind of sits on this Hilbert scheme. Okay, in this case, it's a type of vector bundle. But it's not just a vector bundle, it's also an A module. So it has this extra structure as well, because we're looking at quotients of an A module. Okay, so what that means is that firstly, we're going to look at this minimal resolution, which we've written as a Hilbert scheme, H, and we'll look at the coherent sheaves on that. That's some sort of category. And we're going to look at a functor on that. We're just going to look at the homomorphisms from this vector bundle U to, on coherent sheaves, okay? So of course, when you hom U into any coherent sheaf on H, you'll get some sort of abelian group. But you get a bit more than that. And what you get that's a little bit more is that, well, note that all the elements of A act on this U. So as A acts on U, okay, since this hom is a functor also in this variable here, you'll get an A module structure. So if this is a left A module, you'll get a right A module structure on this abelian group. So this is actually a functor from coherent sheaves on H to modules over A. So this is the key point, and I want to kind of emphasize this, okay? So we wrote this minimal resolution as a Hilbert scheme, okay? We knew it existed before, but what's interesting now is we're going to rewrite it in this new form as a Hilbert scheme. And one of the things that we get for free is this universal family, and I want to show you how to use it. And the way I want to say that you use it is that you've got this now, this functor from coherent sheaves on this H to modules over this A. And when you have a functor, basically you have a connection, a relationship between two things. And what's the relationship between? It's between this minimal resolution and this ring here, kxy star g. And most importantly, this involves the g. Okay, so let me just remind you briefly what the McKay correspondence says. The McKay correspondence says that is, if you look at this minimal resolution, okay, so that basically means being a resolution, it's an isomorphism almost everywhere. But where it's not an isomorphism, so that's above the singularity, you'll find a union of projective lines. They're called exceptional curves. And the number of exceptional curves here is one less than the number of irreducible representations of the group G. Okay, so that's a McKay correspondence. It's a lovely sort of connection between here geometry, the number of exceptional curves of this resolution, minimal resolution, and representation theory of finite groups, so this G here. Okay, so what's the connection? How do you connect this H to this group G? Well, it turns out that this functor is the connection. It connects the coherent sheaves on this H, okay, to modules over this A, and well, it's more than just the group algebra, it also has this kxy in there as well. So let me just tell you the theorem which makes this work. Unfortunately, I can't tell you the details of what's going on here or even just define all the things, but I hope it gives you a sense that this connection should be able to tell you something about the relationship between H and this G, and I want to give you a bit of a sense of how it actually will give you the McKay correspondence. So unfortunately, this is not an equivalence, these two, okay, but it gives you what's called a derived equivalence between these two, okay. So it gives you derived equivalence. And then So if you have a derived equivalence, since it's an equivalence, okay, you can look at invariance of that, and one of the invariants you can take is the Grothendieck group. So you can look at the Grothendieck group on this side, K0 of H, and that's going to be isomorphic to the Grothendieck group on this side, K0 of A. And it turns out that K0 of H, from here you can essentially read off the exceptional curves. Okay, so that information is coded in here, the exceptional curves. And here, this essentially, you can read off from the irreducible representations of G. And that's going to give you the McKay correspondence. So that's a very, very sort of both typical and really, really interesting way of using the universal family, and shows you really why this Hilbert scheme is such an interesting thing. And this universal family is really one of the key gadgets that you use. I hope you enjoyed this adventure in pure mathematics.